Are we back? So I started working on this side project that will eventually go into my Infinite Canvas drawing application. Though that's been already a couple of weeks since I wrote this code. Let me just check what it's doing. Alright. So I had this set up as 2 cameras. So wait, let me write some notes. So I had an idea for how to divide space into an infinite coordinate system. Oh, wait. I reorganized everything, so all my stuff is all over the place now. Okay. Hey, Finklum. How are you doing? Been a while, right? Good morning? Yeah, I guess it is. Alright. Me, pretty good. Though I'm still working on this problem. Well, I didn't really work too much on it. So my current idea is that I have like an origin. And then this has some like valid values in this coordinate system. Well, let's say like right here is like -10 all the way to 10. And then values outside of this don't exist. Let's say because it's outside of the range of possible values, like let's say it's binary, yeah, whatever. And then if you want to access values outside of this, then you can go, okay, I should have drawn this a bit further then. I guess my mic still does that. Okay. So my current idea is I have a coordinate system. Let's say this is the origin. And then it can be represented with 3 values. And then for this, this is like exponentials. So let's say this goes from 10 to -10. And then if you want values outside of that, you go 1 up on the exponential scale. This is also -10. And then this, then you can have another point somewhere, zoom on that point, and then have values, let's say like from -10 here to 10, where this is the origin. Let me make sure everything's working. By the way, I plan on writing my own synthesizer. Synth. So I've been studying a bit about like signal theory. Oh, that's cool. And learning about, for example, modular Eurotrack. So you hear the background sound? Let me put it a bit louder. This is not nature. This is synthesized audio. With like made up animal sounds. Made up wind and everything. I think this would sound good in Rashtal. Something like that. And this is like procedural. So if I can learn to do this... No, I didn't make it. Some 18-year-old guy made it, and then he made a video to explain how he did it. I could post the video on the server, the Discord server. Anyways, so if I learn more about how everything's done, then I can recreate things like that. Anyways. Now what I'm wondering, so I have a camera. Let's see how I set this up. My main goal would be to have, instead of having many cameras, only need one. That would be really cool if I can do that. So this camera, oh wait. -3. Is that where I do this? That's the only difference and every... I never figured out this issue of the mic doing weird noise. I guess it's sending a signal. Very annoying. All right. Oh, there's a 3. Oh, that's a shortcut. Right. Wait, what? coded this like I think 4 weeks ago. I already forgot because I had many iterations on this code. This one was pretty much blank slate though. Okay, so I have 2 squares and then a circle. Circle is here, camera view 2. This is from my library, right? Oh, I was starting to do this. Okay, a coordinate system. Offset cam parent. So if I have so I think, okay, you have like this global space where you can put things. I could like make them be a different color for the demonstration. So yeah, I can put like various objects somewhere in the world. They all have a coordinate system. And then I think I need to have a way to convert them from this into local screen space. Essentially bring whatever value they are into local. That way I can just have one camera draw them. Okay. Camera parent. That was an int. So that's the coordinate. Okay, let me just see. Wait, I have coordinate and then a bunch of things. Let me just create something new then. We'll call it just a coordinate. Is that allowed? Okay, draw. And then a coordinate is always relative to its global space. So I need to know like which, okay. So the current exponent. Okay, so first, no need for camera. No need for a parent. Okay, so we need for, okay, for now I'll use float, it's fine. I'll rework this later. Okay, so this is the XY, so where you are. So let's say like either you're at 0 or yeah, XY axis. And then you need the exponential to know which like system you're in. But then you also need to know from where you're zooming in. So like let's say this is the range. if you want to go somewhere outside of this range, essentially you need to like, there's a translation. So like this origin is 0, 0 on every exponential. So like 0, 0 at 0, 0, 0 at 1, 0, 0. So it's the same coordinate no matter how zoomed in or zoomed out. Yeah, you are. That's the origin of everything. And then from there, you can get to any other point infinitely just by zooming out, doing a translation, and then zooming in. So this is 0, 0 everywhere. And here maybe this is, let's just write let's just say this is 5. And then I guess also 0. But then how do you know where you are? How do you know that this 5, 0 is not here? Oh wait, I wrote this wrong. So this is 0, 0 within this. Okay, that's the thing. Okay. So how do I know that this is a different 0, 0, 0? So you know because you are in, let's say 5, 0. And then this is 5, 0 of the 1. Like that. So this is 0, 0 based on the origin point that's on the higher plane on 5, 0 on the higher exponential system. So I was trying to avoid this because the further out you are, the less precise you can zoom in on a specific point. So essentially, you can't, like, let's say you're zooming out really far. Let's say this is like -10 all the way to 10. And then you're trying to zoom in somewhere. It's kind of hard to explain, I guess. I guess it's, you need to go in. I need this to be as simple as possible. Hey, Adepoken. Yeah. XY. Ah, man, this is so confusing. To do something that, like, you want it to be simple, so it's easy to code, but also it doesn't take long for the code to iterate, like to find what, like everything that's where you're looking at, even though the coordinate systems are always getting rescaled. So you end up with like a bunch of things to draw on the screen, and they all have a different coordinate system. I wonder which version I'm on. Oh, it's new Mono game, that's funny. Okay, so coordinate. It wouldn't have draw, but whatever. X, Y. I guess it would be just exponent. Or do you need the exponent? Okay, so you're at 0 from the 0, 0, 1. You offset by, you translate by 5. So you end up with 5, 0, 1. Then you zoom in, and then you have access to the coordinates in here. And then if you want to do the same thing, like let's say there's a -10 here, then you have a dot. Let's say this is like -5. I guess I'm higher. Let's just say I drew it on the 0 line, it's fine, and then -1. Okay, maybe I should just solve it. Hey, welcome, Calo Slim Game. Okay, so I should solve it for all the points around the origin first, and then think about points that are outside. So around the origin you'll have like pretty much infinite precision. Then it's what do you do to have the same infinite precision but on the XY axis? Okay. So for now, I only need x, y, and then the exponent. Hey, is there a way to compute the error? In a floating point number? Like, let's say you're lacking precision. Is there a way to express the precision loss? Let's see this. Maybe it will answer. Floating point numbers. Man, I used to compute floating points by hand at some point. Floating point numbers have limited precision. If you're a game programmer, you have likely encountered bugs where things start breaking after too much time has elapsed, or after something has moved too far from the origin. This post aims to show you how to answer the questions. What precision do I have at a number? When will I hit precision issues? First, a very quick look at the floating point format. Sign bit, whether the number is positive, exponents, the magnitude of the number, mantissa bits, the fractional bits. 32-bit, man, this page is kind of pissing me off that it does that. 32 bits use floats use 1 bit for sign, 8 bits for exponent, 20, yeah. Whatever number is encoded in the exponent, you subtract 127, yeah. Actual exponent, meaning it can vary from this. 64-bit doubles use 1 bit for sign, 11 bits for exponent, and 52 bits for mantissa. Whatever number is encoded in the exponent bit, you subtract to get the actual exponent, meaning the exponent can be from whatever. 16-bit half floats use 1 bit for sign, 5 bits for exponent, and 10 bits for whatever number, yeah. For all of the above, what am I working on? I'm working on, so I coded this drawing application that's, you can like zoom in, zoom out, draw anywhere, or like draw anywhere here. But as you can see, I limited how far I can zoom out or how far I can zoom in. Because if I just uncap this, eventually you run into floating point number issues, and then the lines will start to jump around because the computer, the computer can't express the number with like the limited amount of bits. So one solution is to increase the amount of bits, so go from like a float to a double. Then at least the issues will arise later. But let's say I want to allow for true infinite drawing on the zooming, so you can allow uncapped zooming forever, or so for out or in, and also uncapped panning on the X and Y axis, so you can go forever. So yeah, that's what I'm working on. And this kind of issue is related to floating point precision. Being able to express numbers with infinite precision, essentially. So my current solution to that is to have a way to express the X and Y, and then an exponent. So then I can at least have numbers around the origin. So I can zoom in, then I'm in this sort of plane or whatever, and then I can say, okay, this is at exponent 0, like if I'm here, exponent 0, then this is 0, 0, 0. Then here, between minus 10 and 10, here is minus 5, or maybe minus 7, or plus 8. Or if I zoom in, then maybe now it's from there. I should use my pen. Let's say I'm zooming in. Then this is like the new minus 10 to 10. Then now 0, 0 is here. Maybe minus 5 is here on the x-axis. Or maybe 8 is here. Anyway, so I'm able to zoom in or out and then have infinite precision. At least within like the exponential. So 0, then 1, 2, 3. So, but like this is gonna be so huge, you'd have to zoom out or zoom in forever. Like not forever, but like it's good enough. But now the issue is like, how do you do the same thing on the X and Y axis? That's where it becomes hard. For all of the above, an exponent of all zeros has the special meaning exponent 0. And this is where the normals, subnormals come into play, and all ones has the special meaning infinity. The exponent bits tell you which pair of two numbers you are between. 2 in the mantissa tells you where you are in that range. What precisions do I have at the number? Let's look at the number 3.5. To figure out the precision we have at that number, we figure out what power of 2 range it's between, and then subdivide that range using the mantissa bits. 3.5 is between 2 and 4. That means we're dividing the range of 2 to 4 using the mantissa bit. A float has 23 bits of mantissa. So the precision we have at 3.5 is the math 0.0. 3.5 itself is actually exactly representable by a float, double or half. But the amount of precision numbers have at that scale is that value. The smallest number you can add or subtract to a value between 2 and 4 is that value. That is the resolution of the values you are working with when working between 2 and 4 using a float. Using a double instead, so you have 0, 0, 0. Using a half float with 10 bits of mantissa. Here's a table showing the amount of precisions you get with each data type at various exponent values. NA is used when an exponent is out of range for a specific data type. So let's look at the half. So between 4096, 8000, you can add at the smallest number you can add is 4. And then here 32, and then here you can't. Yeah. So a quick note on the maximum number you can store in a floating point number. By looking at the half float specifically, a half float has a maximum of exponent of 15, which you can see above puts the number range between 32 and yeah. The precision is 32, which is the smallest step that can be made in a half float at that scale. That range includes a smaller number, but not the larger number. That means that the largest number of half float can store is one step away from the high side of that range. So the largest number that can be stored. How many digits can I rely on? Another helpful way of looking at a floating point precision is how many digits of precisions you can rely on. A float has 23 bits of mantissa. 23 bits lets you store all 6 digits number or lower and most of the 7 digit number. This means that floating point numbers have between 6 and 7 digits of precisions, regardless of exponent. That means that from 0 to 1, you have quite a few decimal places to work with. If you go into the hundreds or thousands, you've lost a few. When you get up into the tens of millions, you've run out of digits for anything beyond the decimal place. You can actually see that this is true in the table in the last section with floating point numbers. 23. 8 million to 16 million, that the precision is at 1. The smallest value that you can add to a floating point value in that range is in fact 1. It's at this point that you have lost all precisions to the right of the decimal place. Interestingly, you still have perfect precisions of the integers though. Half floats have 10 mantissa bits, so they just barely have 3 digits of precision. Doubles have 52, that means double. This can help you understand how precision will break down for you when using a specific data type for a specific magnitude of numbers. When will I hit precision issues? Besides the loose rules above about how many digits of precision you can count on, you can also solve to see when precision will break down for you. Let's say that you are tracking how long your game has been running in seconds, and you do so by adding your frame delta in seconds to a variable every frame. If you have a 30 FPS game, your delta is going to be 0.033. Adding that each frame to a float will eventually cause the float to reach a value where that number is smaller than the smallest difference representable, smaller than the precision, at which point things will start breaking. At first your accuracy will drop and your time will be wrong, but eventually adding your frame delta to the current time won't even change the value of the current time. Time will effectively stop. We'll start with the formula we saw earlier and do one step of simple algebra to get us, how we use this formula. Range. How we use this formula how we use this formula is we put the precision we want into precision and we put the size of the mantissa into mantissa. The result tells us the range that we'll get the precision at. Range equals that times that. This tells us that the range of the floating point number where we'll have our problems. So we'll have to go another step. We'll need to find what exponent has this range. Looking at the table earlier in the post, you might notice that the range at an exponent also happens to be 2 exponent. That's helpful because that just means we take log 2 of the answer we got. Looking at the table again, we can see that floating point numbers have a precision of 0.03125 at exponent value 18. So exponent 18 is close, but its precision is smaller than what we want, aka the precision is still okay. That means we need to seal the number we got from the log 2. Doing that, we see that things will break down at exponent 19. Store integers. Floating point numbers can exactly represent a large number of integers. In fact, exactly store all integers from -2 to can store all between minus to that. And for floats, 16 million to 16. For doubles, it's 9 something. Doubles can in fact exactly represent any 32-bit unsigned integer, since 2 to the power 32 is 4 billion. Oh, are there comments? Okay. Is that that's the guy, okay. Longer would mean a more precise number, but smaller representation, because shorter mantissa would mean the exact opposite. Less precise number, but more space for exponent. Oh, that thing has so many things. So many dates. Another idea I had would be to send like a sort of ray at any angle, but I think I still have issues. Did I have 0, 1, 2? Let me just try that. Okay, I preset some zooms. Wait, was there a 0 for real? No, okay, 1, 2, 3. Okay. So the goal would be that I don't need like dragon, like I only need one of those. And then the camera, only need one camera. If I can do that, that would be the best. But then the camera's coordinate system. Wait, can I? I almost feel like I have an idea. So to have the most precision, the camera's coordinate system XY exponent has to use the smallest exponent, because obviously like on a bigger scale your X and Y, they'll jump over more, like a bigger gap, so you lose precision. So if you're zooming in, then you can be more precise in the the translation, I guess. But you also need stable coordinates. So is there like two problems? One problem is like, how do you represent all the coordinates in a stable coordinate system that has infinite precision? So let me zoom here. So it's easy to have infinite precision. Let's see. I'll just draw boxes. Um, so this here will be understood that it's like the min value, max value. And I guess I put a dot here in the middle for the origin. So inside of this, you can have like infinite. You have like. Okay, so let's say you're zooming out. Now here it is. And then zooming out. I'll draw a bunch just so that I can visualize this better. Oops. I kind of like. I forgot how I coded the line thickness. So this just shows all the areas that you have infinite precision, pretty much. So the more you have more precision where there are more, if you're inside the most amount of those squares. So essentially down here you have like the most precision, and then like already here you have a bit less precision, and then here a bit less, and then here a bit less. So like if I zoom in a lot, I have less precision than if I was zooming in at the same scale here right now with this system. I'll just draw a few more. So I want to be able to solve where the translation, like further from the center, would not lose precision. The issue is that you have to know where... Oops. I got an idea actually for doing lines better. Huh. Yeah, that would work. Let's say like you have this circle, and then once you're happy with the size, then you draw the line, and it shouldn't change after. Do I go fix that really fast? I'm in main. Draw thickness. So when I'm holding shift, that's when I'm drawing a line. Where is shift? Redo all. Thickness. Line. Is tablet drawing pressure? If line is pressure equals a max pressure. If line is held. Essentially, it's when I do the click on the line, it should... Last pressure equals max pressure. What was max pressure? I forgot already. If that... Like the way this was coded was for being able to adjust this thickness. Let me change to this one. adjust the thickness while I was drawing the line. But now I'm seeing that it's awkward. Okay. Max pressure. Max between. So I want to get rid of this. I guess the issue is that if I'm drawing and releasing too slow, like that, slower than 300 milliseconds, I'm able to ah man, I'm getting sidetracked, rip. So max pressure is used here. In other words, what I want is to be able to lock the pressure when the line is pressed. This is when tablet pressure is 0. In other words, then last pressure is used here. If it's not valid, cursor, last tablet pressure, last pressure. I should have put some comments on this. I guess it's because we don't know if it was valid. Else there. And do I have a bool somewhere in here that tells me we went through here? I guess it's just valid. Is there a valid in here? I guess not. Tablet pressure equals 0. So it's set to 0 here. This is in draw, right? So I guess for the line, it's always max pressure. And then when line is held, max pressure. If you release the line, I guess it's because if I don't move my cursor, then it would get is valid. So you don't get new move next. So this stops updating. If it stops updating, so you're updating, you're getting a max last time. If it stops and then it resumes, that's how you get to update the pressure. But how come I'm able to lower it? Like let's say I have this, I can do this, but I can also lower it. Hmm. If that minus that. Oh, I guess because if you're smaller, but then if you're bigger, you go through here, which resets max pressure to be something else. So if you're changing faster than 300, it's not gonna update, or it's gonna update only if you increase. Otherwise, it's only gonna you can decrease if you go through here. All right, yeah. So maybe I figured this was a better feel. Because it allows you, like let's say you start a line and it's too thick, then you can decide, okay, I want it a bit thinner like that, and then it's gonna stay like that. Or if you start it really thin, I guess maybe this is fine. This is maybe, that's what I had in mind when I did it. It does give me more control. Instead of having to decide it at the start here, and then it's locked. Whatever, I'll leave it for now. Alright, back to this. Let's just do more, I guess. I just feel like I might get some insight. Ah, shit. Okay. That's trippy. Oh. Alright. So I can draw everything correctly here, but how do I keep precision here? Let's do the same thing, draw, but from a different location. Was this like the most zoom in that can be? Oh, you see here, there's already a bit of floating point issues. You see how the lines are like slightly jumpy? So that's what I'll eventually solve with this work. Yeah, they're a little bit jumpy between the... If I allowed a little bit more zoom, it would be like really noticeable. Anyways, let's zoom over here. Let's go in this one. I'll try to be on the same y-axis, roughly. Okay, let's go in here. And let's do the same thing in a different color. Maybe blue. Okay. So that will represent a zoomed in point from a different origin. If I can solve this, then this is awesome. Then I can have for real infinite precision. Oops. Yeah, that's the issue with the code for the thickness. So I guess I'll rework it then. Okay, do I leave it there? So because this is a bigger area, you have less precision. So you can't actually define... You can't point to this center here from up here. There's not enough precision to do it. So that means... How do you do it? Or like even worse from like up here. So that means you have to zoom in a little bit on a center that is the closest to this one. So let's say you divide this space into a grid. Then you pick a point that covers... Okay, I'll keep drawing then. Then it will become a bit more obvious what I'm trying to do. But it's kind of annoying because then you need... I'll move it a bit on this side, it's whatever. So I guess there's no solution that doesn't have many translations. So you zoom in, you translate a little bit, and then you... So, but if you have many translation, then it becomes computationally expensive. I'll do the last one, I guess. So in other words, the system has to, like the algorithm needs to find a way to translate the least amount of times. Unless... So the solver thing, whatever the thing that it's trying to solve is how to go from this center point, this origin, and then go from here all the way to here. How do you translate to be able to pinpoint this zone? How do you go from this coordinate system? This one has infinite precision as long as you're like zooming on this center point. Likewise, this here, this whole area has infinite precision as long as you're zooming in on here. So then all the values here are infinite. But it's when you start zooming in somewhere that is not on this origin that you lose precision. So then it requires a separate system. So the code has to be able to go from one origin to another origin. And then so like one way to do it is like you do a translation, zoom in a little bit, do another translation, zoom in a little bit until you can find a coordinate system that can pinpoint this. So explain differently. Explain differently. I can have, let's say, an origin here, a point here. Oops. If, yeah, this is annoying. Let's just do 2. Okay. And then let's split this into 5, I guess. Is fine. I don't care about the y-axis. Likewise, this can be split into 5. Okay. So in other words, maybe I'll use a different, darker. So from here, sure, I'll draw this one too. For these types of line, being able to adjust is nice. Okay. So this allows me to, maybe I should have done 7, whatever. 5. And then like, let's do the same for the smaller one here. So if a point lands on these, then you have infinite precision to zooming in or out. So let's draw it in blue. So I have infinite precision on this blue point. I forget which one I take. Oh well. Five. This is all just to help me visualize. Alright. So this is fine. But if you can't represent a point, so all the other values in between cannot be represented infinitely on this origin. So as long as the origin you're zooming in on is aligned to the grid, you're fine. If it lies somewhere else, then you can lose precision. Unless you allow translating twice. Which is expensive. But I guess there's no way to go around that. I mean, that is true, I guess, if the ratio between the different scale levels always lines up. Is this a problem that's solved by having like the scaling that is different? Or is that wrong? Essentially, you don't want the grids to align. And then if they don't align as you're changing, then it's likely you can find... I don't think that's correct. That has to be wrong, right? So I guess the way you can end up at a bad precision is if you zoom in and then move the camera a little bit. At that point, you're fucked. If you zoom in more. But then this translation tells you the path you took to get to that point, right? And the camera has to have like this translation has to line up already to the grid that you're in. That's a problem that I should probably do on a 1D just to demonstrate. In other words, let's say this is what you're working. Okay, let's say you have a 1D line. And I guess I divide it by 5 again. So then the camera snaps on this point. So this, if you translate, snaps to that, bam, snaps to that, bam, snaps to that. You don't have floating points in here. Bam. Then let's say I'm here. Then I zoom. Then I get to some value, whatever. Let's say it's, so I zoom in. And then I translate, bam. I zoom in on that. Let's say I do it like this, whatever. So this one lines up to that because you're zoomed in. Divide by 5. And then if I zoom, I go here. Then I can, let's say I zoom in more on this one. Zooming out, I ended up somewhere that is outside the value of my range. Outside the values of this grid. So I guess so at that point, let me do one more. I'll use this one, I guess. I feel like I'm really close from solving it. So the path was here, here. Oops. Do I just do lines then? So there's a bunch of translations. So how does the camera work then? And how do you define this point here in the global? So you have, I guess, to... So I guess this point has to say... Okay, wait. So this is 0, -1, -2, 1, 2. When you end up zooming in on that, this is another 0, 1, 2, -1, -2. Then here, on this line, this is 0, -1, -2, 1, 2. 0, -1, -2. Okay. So how do you call... And I guess I'll put a dot here. So the dot that I drew is at point 1 on this line, on this coordinate system, which is at the... So the long way to write this point, I guess, by doing the different steps for this point. So I guess you're at... Okay, I'll do it as a list for now, even though that's what I'm trying to avoid, but I guess I can't. So this is... okay, I'll write it from this side then. 1, 1, 1, -1, 1. So this is... So the more precise you want to be, the more you end up with... Like, the more this coordinate grows. So that's kind of expensive. But maybe it's fine, right? Because... Let's say okay, so I move my camera, boop, boop, boop. That allows me to draw here in this coordinate. Then I zoom out. Poop. Let's say I move. I guess in one way you're trying to relate points to each other's, right? If you want to draw them together on one screen. Maybe this can be simplified. At least depending. So to be able to draw precisely, the camera has to use the lowest coordinate system. Then you can zoom out of that point and then still draw like correctly in this coordinate or this coordinate or this coordinate. And then, so let's say you're zooming out. So now you're on this point, but if you move the camera, then let's say it's gonna snap to this coordinate. So you can purge this from the camera coordinate to be at 0 and then 1 as you're moving. Okay, so let's just draw it for... I'll use orange. So let's say there's another line here. Or maybe I'll go from the 1 just so that it's easier to see. Let's say it's here. this here. -2. Okay. So let's say I want to draw here at -1. So the -1. Oh, maybe I should have written this in the blue color. Too late now. So at -1, I'll draw this dot. And then that's -1, -2, -1. 1. And then what is this 1? So I guess since they share this last 1, then we only care about the 4. Because they share, so they share the bigger coordinate system. So to relate those 2 points, you don't need everything, you only need this sub 3 right here. Sure, I'll draw the other path. Okay. So do you need to draw at the correct precision or not? And then if you're zooming out too far, the lines become invisible, right? Because you're like too far, you can't see them, you don't have to draw them. So a camera can see a range. So you want to draw always at the highest scale that's possible to represent the line you're drawing. And then if the line is like more precise, then you have to get more precision, but otherwise you don't need to. You know the precision based on the camera's zoom level. Essentially, as you zoom in, the space redivides itself, like the grid becomes finer. As you zoom out, the grid becomes coarser because you don't need as much precision to represent what you're seeing. If you're moving the camera at a specific, so let's say I'm in this coordinate system and then I move the camera, then if I zoom in, the space redivides and then the camera moves based on this finer grid. So as you zoom in, it's based on this finer, but then you don't care. I mean, you obviously need to know the path you took. So like from this bigger scale, you went to 1 and then -1 and then 1 and 1 and 1. And I guess in order to relate everything together, you always need to know the global origin, the 0, 0. This is the origin where, like, around this you can So you have one global origin. Then you have like different local origins. That's also fine. So the part that's the same, this big one, let's say, and I'm not I guess in practice you need, so this is 1D, but you also need to know about like this is, I'll just put it under. This is 0, -1, -2, -3, -4. This is 0, 1, -2. I should have written this in red, I guess. -2, -3, -4. Okay. If you zoom out, so how does it work? Does it work the same? Let's assume that this is my global 0, 0. So if I zoom out around this, I can always have perfect precision. What happens if I zoom out, move on this bigger system to 0? So I guess it's a coordinate system that needs two sides. One side for zooming in on the 0, 0, and then one side on the other side of the 0, 0. So the data is like two lists. That way you know where you're at on the 0. So you can insert values either on this left side, the negative side, or on the right side, the positive side. But you need to know which one is 0. Like the root, the thing that makes everything else. I guess this was like an obvious solution. This works, it's just slow. And the more you draw at like coordinate systems that are like incompatible to each other, the more annoying it is to work with. So let's say like you're here and like the camera is in this coordinate system, and then you get out of the bounds. Then you have to like backtrack, go up, find the next one, go in. That always works, right? If the coordinate system covers it. So this is pretty much a month. So you're here. 2. If you go there, then you end up at like the next -2, -1, 0, 1, 2, -2. But then on the scale on the upper one, it increases. This is not too hard to code, I guess. So a coordinate, you need to know. It's just that this is expensive. This is a 3, I guess. So I guess for each point, like wherever you're drawing. Is it just a matter of having trees and then the sub trees, like the children? But then this point, I guess it's a question of like, how do you save this if you want to then recreate the tree? And I guess that's what I had before the parent. So like, let's say you give an ID to each one, and then you say this is the point at 1 in the parent ID of this one. So by having this, I don't need to save the whole tree. I just need to have the parent initialize first, all the way to the smallest stuff. And then if you want to write out the whole coordinate, then it's something similar to that, but with a list on one side for the negatives and then a list on the other side for the positives. And I guess you're able to skip, right? To only get the trees that are important. -4, -3, -2, -1. Like, let's say you're zooming in on -1, and then you're zooming in like on a smaller scale without moving, and you're still around that origin. I guess I can draw that for now. So -1 here. 3. Just draw that. And then zooming in more. And then zooming in more. Alright. Maybe I should have used a different color. Anyways, so let's say this is where I want to draw. 0, 1, 2. And then my dot will be -1 here. So I'll draw this here. So we go to get to this dot. Oops. You go down all the way to 0 here. And then you can move to the side for the 1 here. Is that how I was drawing them? I guess I didn't need to do this one. So we're at -1 at some scale. This is what, 0, -1, -2, -3. Oh, I guess I spread it out more, but it doesn't matter. So let's just write this -1, -3. That's centered on -1, 0. Right here. So this one didn't need to go through the -2 and the -1. Maybe it should though. If I write it out, let's see what it does. 1, 2. Then you're going to like 0, -2, and then 0, and then -1, 0. So when you're at an origin of 0, when you're at a 0, the 0 can drop. Is that what I'm getting? -1. The 2 zeros can be dropped. Because it means you're still on this -1. Everything lower is on the origin that is the -1. The local origin 0. Okay. I'll be right back. I should go eat soon. Starting to starve. So this is the system. I guess I have to accept reality. So this works. So now I have to like learn how to work with this so that it's easy to code. And is it better if every single I mean, this is the absolute coordinate system where you can precisely, by using like this infinite list idea, this is precisely, you can have any value infinitely because you have infinite, like unlike floating point numbers, this is a list, so you can have any amount of value. The issue is that it takes more data, but I guess we don't care. Then after that, it's a matter of converting this into something that's usable for drawing. Something that can still be fast. So then that's a matter of converting this value into something usable. So every time you zoom out or zoom in, that's when, so essentially you're taking the values and then bringing them into this local coordinate, like this camera, this viewpoint, or whatever. Depending on how far you're zoomed in or close, in the camera coordinate system, you have more or less precision. So some some lines can be drawn. If you're far away, you don't care as much about the precision. It's when you zoom in, like you don't care as much for the precision of a single point. Like let's say they're 1 pixel off, you won't notice, like it doesn't matter. But if you're zooming in, that's where it matters, that the line still stays, like let's say in the screen, within 1 pixel of where it should really be in the global coordinate. So depending on how zoomed in, you're looking at a different way of subdividing the space. So this is like a game of how do you quickly take a global coordinate and bring it into the screen. And then as we can see here, if a coordinate shares, I guess in practice it's not really a comparison between 2 points, it's a comparison between a point and where the camera is right now. So if the camera spans, I guess there's a part that's optimizing. For example, even though the path, like to go from to this point, like we went to the 1, 0, 1, -1, -2. I guess there's a way to divide space. So there's like ambiguity, I guess. Because you could have gotten to this -2 by going through the center point, 0, and then spanning, and then like rescaling from there to get to the -2 from a different path. Yeah, so there's like, if you can, you want to have points that are the closest path to the 0. So for example, here, this point is ambiguous given, so like, how do we like represent that? I'll use yellow, I guess. And I'll draw it like really small. So like 0. So I'll just draw it like this. 0. And then from there, 0. This gets divided like this. And then from there, you have, let's say, it's kind of hard to draw this in a way that's readable. And then, so this, I guess it's divided like that again. And then 0, let's say we're going to this -1 here, yeah. And then this here. This one is supposed to be equivalent to this one, and then this one is supposed to be equivalent to this one. And then I guess I'll do one more here. Ah, shit, I have to... Okay, so... So this is, let's say, layer 0 minus 1 minus 2 minus 3 minus 4. It's kind of hard to read this data, but whatever. So now this is 0 minus 1. This one is like minus 2. This one is minus 3. Then we're at the minus 4 down here. Let's just draw it again. So this is all the way, let's say here. I guess it's minus 4. I'll just draw it again, whatever. And then technically, you can have this minus 1. Okay, well, the way this is done, the minus 1 here is equivalent to the 0. Kind of small, but whatever. So this one is the same as 0. I guess that's insightful then. I'll draw it the same way. And then 0. This is all going down 0, right? Except 1. So 0, 0, 0, 0. And then I guess 1. Oops. So these two, minus 1, minus 2, minus 1, 1, 1 is equivalent to 0, 0, 0, 0, 1. I'm not entirely sure how to know that. So yeah, there's ambiguity in this system, the way it's designed. I don't know if it's possible to not have ambiguity. I guess one way to not have ambiguity is to... I guess you can figure it out because this here at minus 4 goes over the boundaries of the coordinate system in minus 2. So you need a value that doesn't exceed the bounds. If you go over the bounds of like a higher, I guess that means there's a, like let's say it's divided -2, -1, 0, 1, 2. Then it means, hey, welcome THC, hey, long time no see. How are you doing? What is share the love? Oh, that's fun. So as soon as I go over the bounds, it means that I can backtrack. Bam, I'm backtracking all the way here, which brings me to 0. So then I move from the 1 here down left 1. Then I'm able to go all the way. Okay, interesting. So it's like a funnel, you can pretty much say. The values smaller have to stay within the bounds of the parent. I didn't finish my game yet. I'm taking a slight break, I guess. I'm working on this side project. Though I think this has more value to the world after I'm done with this. It's an infinite canvas drawing application. And but then once I've solved this, it can be used in a lot of other stuff. Like anytime you need similar, yeah, it's similar to Milton, though I think I like it more already. It's more like user friendly. It's easier to like pick colors, change like the background if you need. You can define your own color scheme. A lot of features. It's actually called Mitten instead of Milton. Check this out. It's called Mitten. A lot of stuff can be controlled with hotkeys. Yeah. Camera control. I can like save camera spot. Oh. You see, I can like save where I was and then also save another spot. I guess I saved this at some point. I saved this one here. There's animation, so the zoom is more smooth. You also have a little indicator on the side that shows you like how far you're zoomed in. So it's easier to like go back where you are. So you could actually use this already to do PowerPoint presentations with like drawings and then being able to switch between screens. Oops. You see like this. Oop, oop. What do I have? There's undo. You can undo all the way back to the beginning. Full screen mode. Oops. I guess it doesn't really change much, and because I'm already almost full screen. You can save files. Oh yeah, that's true. There's a slot 0. So let's say you're here. Right, so let's say I move somewhere. I can toggle, so let's say I'm at position 1. I can, where is it toggling from right now? I'm not entirely sure. Here I'm toggling between this spot and this spot. That's kind of funny, I forgot how I coded this. but it can allow me to work in 2 spots at the same time. Let's say I'm drawing here, and I'm drawing here, and I can move my camera, draw around here, go back here, draw around here, move a little bit. Wow, that's kind of cool. You can toggle really quickly between 2 spots. So let's say I'm drawing like a bit on the side here, and then a bit on the side here. So yeah, it's a lot faster. Like let's say I'm working down here, and then I also want to work up here. Then I can like switch between the two. So what am I working on? So right now the zoom is limited. So you can see if I zoom in, there's a point where I can't zoom in more. Likewise, if I zoom out, there's a point I can't zoom out. Hey, Tatak. What's up? I'm still working on this shit. So yeah, if I zoom out. So right now it's like the code is set to cap the zoom because otherwise you run into floating point issues. So I want to design a system that allows me to avoid floating point issues while having a true infinite canvas. And then the main idea is that you can pick a point that you call, let's say 0, 0, and if you don't pan your camera at all, so like do like left, right, up, down movements, around this point I can have infinite precision around the point 0, 0. You can represent a coordinate by an x and y, and then an exponential. Oops, I have too many things open. So if here, like this square represents a sort of plane, I guess. So you have access to a range of values. And then within those values, so like this is all like a little grid. So you can have like, and then as long as your points align to the grid, you can have infinite, you have like the precision of that grid. And then for every spot like this, they also have a sort of precision. So they all have the same thing. Like even here, this bigger one has like a grid inside. So around the center origin, if you just zoom in onto like this dot and you never move the screen, then you have infinite precision. But I need to have this work if you can move the screen. The floating origin, yeah. But like the issue is that how do you represent a point that is elsewhere? Because on the bigger grid, you have only some, like here this is 1D, it's the same thing. But essentially, the deeper you go, the less, like from the bigger grid, I guess this one shows it, like this is a path. So let's say your center is on 1, then you zoom in. So this is, let's say as you're zooming in, this is like 0. Then you can move your screen, end up at -1. So that's like a translation. You translated 1. This one here doesn't have a value in this bigger grid. So you have no way of going from this bigger grid into -1, into this point, without like being at 1, zooming in, redividing the grid, then translating to -1. Then let's say you zoom in more, translate to 1, zoom in more, translate to 1. So you see like the values that are smaller, you're taking a path through the coordinate system to be able to, so if you represent this by a list, the more precise you have, the bigger this list grows. That's like the cost of having to do translations and then being able to zoom. So this here, just to make sure you understand, like this is a coordinate system that cannot represent -3. -3 is out of bounds. 3 positive is out of bounds. So if you want to go to 3 positive here, in reality you have to zoom out, have like the a bigger coordinate system. Let's say it's this. And then like translate to 1, and then 1 here can have its own little grid that represents 3 somewhere. Oh, I mean this, I guess 3 would be this one. So essentially you zoom out, go into this bigger system that's like on the exponential scale. So this is 1, this here on the exponential scale is 0. If you zoom in, it's -1. So the 3 minus. Oh, I guess I drew this. Like the drawing is not precise. So the 3 it would be. Yeah, whatever. Don't anyways, like you have to zoom out onto a bigger coordinate, translate, and then you can zoom in and then do your own translation until you get to the precise point outside of the bounds of 2 here. But like, so while this works, it's not really fast. When you want to draw everything. So now I need to have a way to like convert the units. I need to have a way to make this usable. Anyway, so now at least I understand, like I understood this a few months ago already. So like here, this white squares, this represents a coordinate system. You can zoom in infinitely. And then the issue is like, how do you go from this? So the origin is there, like this is a 0, 0, let's say, to like this blue one. So how do those relate? So then you have a series of operations to be able to eventually zoom in on that point infinitely. But like one way to understand this, I think, is... So like this is pretty much the path that your camera is doing. Like let's say you're zooming out, the grid redefines itself so that ideally you have, for every pixel on the screen, the grid would be like finer than the pixel, I guess. So then if you zoom out, then it redivides. Or if you zoom in, the grid redivides. So that you always have enough, like the grid is always finer than the pixels on the screen. So then you can draw everything and it's gonna be precise, I guess. So that's like how you do it to have an infinite coordinate system. You have to zoom so for every value that ends up outside the system, the coordinates, you zoom out on the exponential, then translate onto a different value, and then this can represent values. Then if you zoom in on the 1, then you're able to it's like every value is like a funnel, I guess. So let's say this is your line, then values can be represented. I should have used 5. So if you do this, normally it would be centered, but I don't really care. So it's like when you want to represent the values that are in between the, like these tips. So that's where like the path to get to a different origin is kind of expensive, I guess. So now what I'm thinking about is how do you make sure that a coordinate is unique? So that means you need a few rules on top of this, because then you can get to the same point through a different path, which is not that good, right? To have multiple ways to represent the same point, because then you need more, like you need to do more math to know if the point is the same. So you need to be able to like define a unique path for every point so that you don't have many paths. Then that allows you to assume things in the system and then simplify the math. And then one thing that's like interesting is that for the lines, as they become smaller and smaller, at some point you don't have to draw them because they're too small. And then there's also the case where the line itself can have like this infinite precision thing, but when you're drawing them to the screen, you're drawing them inside of a grid that represents the screen. So if something is really, really precise in the coordinates, when you're drawing them, they don't need to be as precise. Like they can be like, let's say, rounded to the nearest pixels. And then if you zoom in on them, then that's where you don't want to lose the precision. So what I'm thinking is that I need a way to convert these values into the camera coordinates. So as you're drawing, you want to save them into a really precise coordinate. As you draw them, it doesn't matter as much. And maybe that's how I can have a fast system anyways. And then the values. Like querying this structure is kind of expensive. So you want to do it the least amount, as little as possible. Anyways, I should go eat. It's already almost 2 p.m. But I'm kind of happy about this progress. I can almost like understand what I have to code. So you want the camera, like let's say you're zoomed in. Let's say you're zoomed in on the 0, 0. Then as you zoom out, if you zoom back in, you want to still be on the 0, 0. But let's say you zoom out and then you translate. Then if you then instead of like having the position, anyways, I'll think about it more and then I'll try something, I guess. Maybe I can do this right away so I don't forget. So a coordinate is not only an xy, it's an xy at the exponent. Wait, let me see that again. This is in 1D. 0, 0. So this here has no... You don't need this... Yeah. I mean, I'm rediscovering the same thing many times. So I guess one rule in the system is that you need... Like here, this what this shows is this value here, -1, -2, -1, 1, 1, is equivalent to 0, 0, 0, 0, 1. In that case, you want to use the 0, 0, 0, 0, 1, because if you do like the funnel, like this funnel here can already express this value. And then if you're panning like this, I guess I'll reduce. And then there's this. I mean, it's kind of hard to see because I didn't draw like to scale. And then this here. anyways, you want to be using the funnel that's the closest to the origin. So this funnel is more, this path is more complex than this, so you want to use, you want the system to use a path that is more compact, I guess. And then this can be written, the one, this point here, that's can just be written 1 0. Everything else can drop. Offset. So offset would eventually happen when you bring it into the camera coordinate system. So you want like a coordinate system that allows you to express any values infinitely. But then those values are awkward to work with. Like you want to bring them into the camera. That's a little bit like origin shifting. So you want to bring everything into the origin of the camera where you're looking at. So here you can see, like, as I'm zooming out, this shows the exponential. So here when I'm zooming here, I'm at exponential 54. Here when I'm zooming in, I'm at like 0.01. Oh no, that's not exponential. It's the first one maybe? Oh no, that's the number. I don't think it shows. Yeah, whatever. I guess it's this one that would show. Oh, I don't have it. Yeah, whatever. It's logarithm. It's a logarithm, like you can express really small values or really high values around an origin. Anyways, so this xy, I guess that's a coordinate xy. You don't have a draw, we don't care about this. This can be I'll just do this for now. Oops. Can't write. Okay. And then a coordinate system. I guess we don't care about that. It would be like a list. And also, let me just see this again. So if you... Ah man, I can't. Maybe I need to go eat. This is not that hard. If you're at 0, okay, let's say you're at let's say this is the global origin 0 0. You want to go here, so you zoom out. This becomes not -1 but 1. Then you translate all the way to -1 here. I'll just write this temporarily. So this is 0. This is the origin. I guess, okay, I'll just redraw it differently then. I have an origin here. Let's say this is the global origin, 0. 1, 2. Okay. I want to draw something here, but it's outside the range. So then you rescale this. Alright. So this is 0 at exponent 0. This is exponent 1. 1, 2. And then I can go on the side. I'll draw it like this, different color. Okay. They should line up better, but whatever. I guess this would be at 2 maybe. Okay, the 2 is pretty much at let's just do this. 2 is at minus 1.5, right? I'll use. You don't want floating points. Anyways, that helps me like figure it out. Okay, 0. Ah man, this is not hard. It's just because my drawings suck. Okay. Okay, 0. I zoom out. How do I draw my line? Okay, I'll use this one as the 1 and then I'll do the other ones from here. This is 0. I'll draw a few levels so that it's easier. 0, 1, 2, 1, 2. Okay. Zero, 1, 2. Okay. So let's say this is 0, 1, minus 1. And then so I need my line. Minus 1, 2, minus. Zero. Oh, what did I do? 1, 2. Okay. This is at 2. So now let's say we rescale on 1. So the way this is drawn, I drew it a bit above, it's fine I guess. 1, 2. Wait, what? I think it's correct. Okay. Then here. Zero, 1, 2. Okay, this is at 1, 2. Wait. 1, 0 rather. And then minus 1 is here. Okay. So at 0, so the path from 0 all the way, let's say, to this 1. I guess to this -1 would be better. So there's 1. Okay, I'll draw it like this. Green. So you go all the way up here, translate here, go all the way down here, translate here. Or I guess I don't need this last one. So to represent this 0, this -1, you have -1, which is at -1. Then you have -1, which is at 2. That's all, right? I guess I should write out all, even though that's kind of correct, because you don't need all the other info. I'll write out the other one. So you're at 0, at 0, then you have 0 at 1, and then you have -1 at 2. That's all. So the zeros can be dropped. So what does it mean? For writing this code, this coordinate? I mean, that's a coordinate. Is this the correct work coordinate system? I guess it's fine for now. And then this is a list, let's see, of coordinate. That's not a good word. Usually I use set. Forget how to code. I set. Eventually this would not be a floating point, it would be integers. But it's fine for now. This only shows you like the zoom and the translation. So the XY tells you translation, exponent tells you the zoom. But then this doesn't know where it is. This only tells you a step. in the process of locating a point. So if there's like only one in the list, then you're here. So this says exponent 0, 1, 2, minus 1, minus 2. So by itself, let's say it's so let's say it's the exponent is minus 1, then it will think it's here. But if there's something above minus 1, 2, and then 1, okay, add coordinate. Too lazy for that. So you need to add from biggest to smallest, right? Probably that would not be the correct API, but whatever. Was there this in C# now? Maybe I renamed this to because this is kind of a coordinate, right? It identifies a point in space. So then this is it. What is this? It's a list of something. What is like the thing that? What is this? Instead, should I code this as like X, Y, X, and then the ability to have a child? Like, is it recursive instead? Then you can just create your 3 like that. If you need more precision, then you don't need a list. Should I just have a list and recursive structure, and then you can have infinite precision within only this value? I guess it kind of makes sense because how do you call this? Also, should it go the other way? From the child to the parent? Does it make more sense to... I guess it makes more sense to have a global system than one that is based on like a deeper value, something like that. That equals to null by default. But then when you initialize that, should values be standalone? So this one doesn't care, like you're at -2, -1, 0, 1, 2. If it's standalone, then you can drop this value, the -1. There's like so many ways to represent the same data. Like this was one way of writing them out. -1, 1, 0, 0. Recursive data structure. I guess you want to start from the top if it's to be used. Eventually you can normalize that, I think. Drop everything except... Or not normalize, but flatten. The issue is that this doesn't make sense. The coordinate. The exponent. I guess like the exponent is like context about where you're at. But it doesn't mean anything because you don't know if you're at this -1 or this one. I guess it makes sense to start at the top and then go down. You're scaling on that. Man, this is so dumb. How do... Okay, I have this. Because I can't wrap around what I want to do, I guess. I don't know what I'm doing. So there's a million ways of doing the same thing. I guess I don't know yet what I will need later or something. Well, like the way to make this be useful. So right now it's like something, it works, but it's not useful by itself like that. So I guess I don't care then. So you start. So I guess it should be from the bottom parent. Parent can be null If it's null, it means that you're in the origin coordinates. You're not translated. Let's try this. Maybe I put this. I guess this is more important. Can I write? Then this makes no sense. Okay. But now I can do a list of coordinate. What was that? Coordinate space? Oh, from another thing. Okay. I guess I can just do chords. Then I'll initialize this somewhere. It's not exactly useful yet. Okay. And then I can do that's a recursive structure. I'll just create something here. Chord. Okay, so let's just create this one. So this is, I guess I can have 0. Start with this. You're at 0, 0. That's the center of the screen, let's say, or the world rather. You're no parent, that's fine. So the system's goal should be to minimize the size of this tree. Also, do I need a special camera? Just for this specific problem. Anyways, let's also add this 0 here. This -1 rather. So you can do a new coordinate at -1, 0. The parent is what? New coordinate. This one is at -1, -1, 0, 2, no. Yeah, keep it 0 to be on the 1D axis. So I guess there's nothing that forbids you from doing defining the coordinates that are in the same position coming from a different branch. But at least it works, right? You can define. Should the exponent be an offset from the parent? Or does that not make sense? So you go from 0 all the way up to like here, this one went from 2 all the way up to -1. So 1, 2, 3. So would this be -3 instead from the 2 exponent? Or is it better to keep exponents locked to like a global exponent system or something? It's like exponents are fixed in space on this axis. 2, 1, 0, 1. So then let's say your camera is at so how does the camera move? The camera has a position in this global space. Like as it's translating, it's gonna be kind of navigating the tree, I guess. Does it mean that the camera... The thing is that you're not allowed to go over the edge. Like the camera has a span, like a size, I guess. Or does it not have a size? You need to know what you're looking at. Yeah, I should just end and go eat. I have something that's like looking like something. Like it's it's all my boilerplate. So this at the top, you have the bottom coordinate. And then that's the path to go back to the center, I guess. And then if you do it the other way, then it's the path to go to the coordinate. I guess it's not actually a 3 if I code it like that. It's like 1. It's a coordinate in this global 3 type of thing. but it's not a 3 data structure, it's just a 3 for representing this. So you have the camera, and then the goal is to bring these coordinates into the camera, but then the core. Yeah. Anyway, I'll think about it. I gotta go eat. Thanks for watching. Peace. I think that was my first stream of the year. Yeah. I don't have too much time to stream lately. Anyways.